So we're going to be graphing a transformation of a square root function here. So we've got -3. Here we go. G of x is equal to -3 times the square root of x plus 1 plus 2. Identify the domain and range. Describe how it's related to the graph of the parent function, which is just square root of x. So yesterday we were talking about figuring out the domain, and the domain has to do with what's going on underneath the radical, or in this case, underneath the square root. And what did we say about the value under the square root? What type of number did it have to be? Yeah, or 0, right? It could be 0 or more than 0, but it couldn't be a negative. So greater than or equal to 0, which is why we're writing x plus 1 is greater than or equal to 0. So write an inequality using the radicand, set it greater than or equal to 0. Solve for that, so subtract 1 from both sides, and x is greater than or equal to -1, which would be the domain of the function. It will not go further left than -1 on the x-axis. In terms of the domain, we got the domain. In terms of the range, the +2 means that this function has been moved up 2. So the maximum y value. Why is it a maximum instead of a minimum y value? Here, it was a minimum y value, and all the y values were greater than or equal to 1. It got moved up 1. And that is greater than or equal to 1 for all the values of y, which meant that the minimum value on the y-axis was 1. Here, it's being moved up 2, but this time it's a maximum value of 2 on the y-axis. Why is that? Yeah, there's a negative in front of the 3. The -3 transforms the graph by reflecting across the x-axis, which means instead of going in an upward arc, it's going to be moving in a downward arc. So this time our y value is the maximum point on the graph at 2, and it's going to come down like this, as opposed to this one up here where it was moved up 1, but it was a principal root, so it was going to curve upward. Then it tells you to go ahead and use the x values determined from step 1 to make a table. And we start at -1. Why do we not go to -2? What's that? Yeah, -1 is the furthest left we can go in the domain. So going to -2 doesn't actually make sense. So if we plug in values, -1 into the function, -1 plus 1 is 0. 0 times, and the square root of 0 is 0. 0 times -3 is 0. 0 plus 2 is 2. So if x is -1, y equals 2, which is what this shows right here. So we get the point -1, 2. So this is the maximum point on the graph, -1, 2. That's this one right here. And then if we plug in 0 for x, 0 plus 1 is 1. The square root of 1 is 1. 1 times -3 is -3. -3 plus 2 is -1. So we have the point 0, -1. That's right here, which happens to be the y-intercept. If you plug in 1, 1 plus 1 is 2. The square root of 2 is like 1.4 something, right? Multiply by -3, add 2, you get about -2.2. If you plug in 2, you get about -3.2. And then if you plug in 3, you get exactly -4. And that's because if you plug in 3, 3 plus 1 is 4. The square root of 4 is 2. 2 times -3 is -6, and -6 plus 2 is -4. Therefore, you get 3, -4. Now, there is a pretty simple way. Instead of taking these values and plugging it into your calculator and doing everything every single time and calculating it over and over and over, you could just go ahead and go to your graphing calculator, type in the function -3 times the square root of, go ahead and plug this into your calculators on the y equals menu. -3 times the square root of x plus 1, and then we got to move outside of the square root, outside of the radicand, or the radical, and type in +2. We could look at the graph, but looking at the graph is not going to give us the exact values for x's and y's. Does anybody know how to get to a place in the calculator where we could actually look at the x and the y values paired up? If you're in my... Yeah. What is it? I heard somebody say it. Who was it? Second and then graph. Yeah, you look at the table of values. So second graph takes you to a table of values. And sure enough, if you look at an x value of -2, there is no y value because it doesn't actually go that far left. So these are all the values that are on that table. X equals -1, y equals 2, x is 0, y is -1, x is 1, y is -2.2-ish. 2, you get -3.2 if you round it, 3, -4, 4, -4.7, so forth. So instead of typing in the function every single time and plugging in values for x over and over and over, you can type it into the y equals menu and then go to your table of values, and that makes it a little bit easier to get those values. So that's how you can make your life a little bit easier, and it just makes the work faster. That's all. So if you're having to graph it by hand, this would be my suggestion. Get that table open. The domain, here we go. The domain of this is what? X is greater than or equal to -1. The range, g of x or y is less than or equal to what? 2. Yeah. The maximum of this function is -1, what? 2. Yeah. So now we're going to talk about how this compares to the parent function, which is y equals the square root of x. Because f of x, the parent function, is equal to the square root of x, and g of x is equal to a times the square root of x minus h plus k, where a is -3, h is -1, and k is 2. Going back up here, why is h equal to -1 when there's a plus? Yeah, the h is already, we plug in a negative h into this form of the equation. The form includes subtraction. And so if you plug in a negative value of h, you're subtracting a negative, which ends up being plus. So it's kind of opposite of maybe your expectations when you're talking about stuff underneath the radical symbol. And then outside of the radical symbol, it's basically what you would expect. So our value of h is -1, our value of k is 2. So because a is less than 0, and the absolute value of a is greater than 1, that's true for both of those things. The value of a itself is less than 0, it's -3. The absolute value of a is greater than 1, the absolute value of a is 3. The graph is reflected in which axis? A is negative, so it flips it across which one? The x-axis, good. And stretched vertically by a factor of the absolute value of a, which is 3. Because h is less than 0, the graph is translated how many, which direction, left or right? Left. How many units? 1. That has to do with the domain. The range has to do with the value of k. The translation of k is greater than 0, so the graph is translated up or down? Up. How many units? 2. There you go. So it's a lot of writing to do. If once you understand what those values in the actual function do, it's not super complicated because it's a very set thing. It doesn't really change based on what function you're looking at, what those different things do. They always do those things. It's very consistent. And so if you remember what those values a, h, and k do, writing up the translations and the transformations doesn't have to be a super hard and challenging thing, as long as you go back and you just double check and you're like, okay, I got my rules down here. I can reference the rules for down here for what's going on with the transformations. Any questions before we look at an actual example of this being used? So far? Let's look at example 3. Analyzing the graph of a square root function, and this one is talking about blood donations. So, when blood is donated, medical professionals use a centrifuge to separate it. The centrifuge spins the blood, causing it to separate into 3 components, which are red cells, platelets, and plasma. Anybody know what a centrifuge is? Yeah, it spins it, exactly. They use it for medical purposes, and I know at least back in the day when NASA was first looking into sending people into space, they would put people in centrifuges to experience G-forces. They basically put like this little like pod on the end of like a pendulum thing, and they would spin it around, and it would like cause people, it would just cause massive G-forces to like prepare them to be in space. So yeah, centrifuges is just something that spins things to create G-forces, and in this case, it separates out the different particles because I'm guessing it has to do with different weights or mass or whatever is in there. I don't know. Science is not my forte. Anyway, in order to efficiently separate the blood, the centrifuge must spin at a specified rate, measured in rotations per minute or RPMs, much like a car engine, for the required gravitational force or G-force exerted on the blood. For a centrifuge with a radius of 7.8 centimeters, the RPM setting of the centrifuge is determined by the product of 104.23 and the square root of the G-force required. So there's obviously a couple different parameters here. So we got a radius here, and it's determined by the product of this number. Not exactly sure why this number is what it is. It's probably a very long, complex formula to get that value. And then you're multiplying it by the square root of the G-force required, which we're not going to know the G-force required, but we will have radius, and we will have, this appears to be a constant. You're going to multiply it by that every single time. So in words, so we're going to write and graph the function where you've got and then we're going to complete the table and write the function. So the words here, the RPM setting of the centrifuge is the product of 104.23 and the square root of the G-force required. So if you're writing it out in words, this is what we're taking from that paragraph to say, all right, the thing that we are trying to figure out, the setting, is equal to the product of this number multiplied by the G-force required. So let G represent the force and R represent the RPM setting. It tells you we're just going to use G for G-force, and so R is going to go here. And so basically what we're saying is we're trying to figure out what the RPM needs to be for that machine in order to achieve a particular G-force. And so if we know what the G-force is, that will tell us what the RPM settings on the machine needs to be. And so this one is going to determine that one. So we're looking at an independent variable of G and a dependent variable of R. The gravitational force will determine the RPM. The RPM is dependent on the G-forces. So our X values basically correlate to G and the Y values correlate to R. Now, I don't see 7.8 centimeters for radius here. What's that? It's not required, no. If the 7.8 centimeters was to change, my guess would be that this 104.23 would change. But the other things wouldn't, because there's some constant value when we're talking about a radius here. So 7.8 and 104.23, those two things go hand in hand, but I'm guessing the 7.8 determines this constant value in this particular situation. But it's not actually part of the equation. So here's our function. R is equal to 104.23 times the square root of G. So if there are no G-forces, there are no RPMs. Because if you plug in 0 for G, 0 times anything is 0. So let's go to our calculator here real quick. We'll go to the y equals menu. Let's type in this function here. We're going to have 104.23. We're going to multiply that by the square root of X. We can't really use G here, so we'll just go with X like we normally do. And then we'll go to our table of values. And the table of values is going to be quite different than what we've got going here. Now, what would be the point of having such large intervals for X and creating such large values for Y? What would be the point of that? I mean, why would you think to go from 0 to 400 to 800 to 1200 to 1600? Like in terms of our X values, instead of 1, 2, 3, 4, 5. Any thoughts? Well, so I'm thinking the reason why we're getting such large numbers is because it probably has to do with the force required to actually separate the material. And generally speaking, it's going to be large values that are going to do that. I mean, waving your hand around like this is going to create some kind of G-force, but not very much. And so if we're talking about like 1 G-force is basically just sitting still. You know, 1 G is like 1 times the force of gravity, which is what we normally live at. That would be an RPM of 104.23. 104.23 rotations per minute is basically like a heart rate that is slightly elevated, right? 104 is not that many times per minute. If you go up to 2, it goes to 147. It doesn't increase it by that much. And so if you're talking about RPMs, and if you've ever looked at anybody ever looked at a tachometer on a car engine where it shows the RPMs and it gives you like, it says like 1, 2, 3, 4, 5, 6. Sometimes they go up to 7 and 8, but then underneath it says times 1,000. That means it's rotating that many times per minute. So if you think about RPMs generating gravitational like G-forces, things have to spin pretty quickly to actually generate lots of G-forces. So that's why we're using such big numbers here. So let's go ahead and do a little bit of adjusting on here, because we can actually adjust our table of values instead of scrolling to 400 and 800 and all that. That would be really annoying. So it says press plus for triangle table. Triangle just means delta, which means a change. So we can change the intervals of the X values when we push plus. So hit plus, and down at the bottom, it says table equals 1. So the delta for the table, the change of the X values, starts at 0 and it goes up by 1. Well, let's start at 0 and go up by 400. So change that 1 to 400. And then our intervals will be every 400, just like here. And we can actually see that these numbers for the RPM are not exact values. There are some decimals along with those. But we're able to change that table to basically fit with what's going on here. So 0, 0, and then 400 is 2084.6, which rounds up to 2085, and so forth. So those are all our values right here. So 4169, 3610.6, which rounds up to 3611, 2948. So we can see that those match up really nicely. Let's go ahead and change this back to a table equaling 1, though. So hit plus again and change that 400 back to a 1. That way the next people that use it aren't going to be freaked out by what's going on there. So you can set that to the side. So let's take a look here. Our domain. Our values of G are greater than or equal to 0. The range is going to do with R. So we don't have to write this necessarily in set notation like this. We can just write the inequality. So we're going to, the range values are R. What are all the values of R in this particular function? What are the parameters for our range? Greater than or equal to 0, yeah. So the domain and the range here happen to be the same. So 0, 0, because if you look at the function, there are no values less than 0, which means that our x-intercept, where does the graph cross the x-axis? That's 0. So x equals 0. And the y-intercept? Where does the graph cross the y-axis? 0. Yeah, y equals 0. All right. Increasing and decreasing intervals. Interesting. First of all, let's take a look at this. Are there any decreasing intervals on this graph? No. Okay. So there's only an increasing interval here. So we're going to say INC for increasing. Just abbreviate that. On what interval for x values, when we're talking about increasing or decreasing, we're talking about the x values in relation to the y values. So the graph is going up on the y-axis for which values of x? When does this graph start to go in an upward direction? As soon as you get past 0, right? So this would be x is greater than 0. All right, positive and negative intervals. Oh, I wrote G. I wrote X. It should have been G. It's fine. G and X are the same thing in this situation. Positive and negative. So it gives us the answer here. And positive just means where is this graph above the x-axis in terms of x values. So positive y values, meaning above the x-axis, are for all values that are greater than 0. So same answer as this one. It's increasing and it's above the x-axis along that same interval of x values being greater than 0. End behavior. As g goes to positive infinity, r goes to positive infinity. That would be what's happening on the right end of it. How would we describe the left end behavior? Does it go to negative infinity? What does it go to? It goes to 0. So we would say as g goes to 0, r goes to what? 0. So as the x value approaches 0 from the right side, as you go from right to left, as you're approaching 0 on the x-axis, you're approaching 0 on the y-axis. So that would be the left end, and then this is the right end. All right. So it's a lot of individual little things. Hopefully the individual little things aren't super challenging to figure out, because this is stuff that you've done before with other types of graphs. So let's keep going. We got an inequality next. So we are graphing a square root inequality, and this one is pretty much already graphed for us, which is kind of nice. You'll have to do some of these on your own, but first of all, we're talking about the graph of y is less than the square root of 2x plus 5. If you graph the related function, you're basically going to go ahead and just graph the function like you normally would. However, you're going to graph the boundary of this equals using a, what kind of line is on here? Dotted line. Using a dotted line because the inequality is a less than. Now, does anybody remember the difference between a dotted line and a solid line in terms of the symbol being used? Yeah. Let's go ahead and put a little note in case you've forgotten that. Let's do that on the top left here. If you have greater than or less than, you will use a dotted line. Just greater than or just less than is a dotted line. Greater than or equal to, less than or equal to, or less than or equal to, greater than or equal to is going to be a solid line. So this is something that you probably learned back in Algebra 1, maybe even in pre-algebra when you're graphing linear equations for the first time. Now over here, there's something else that we need to talk about that is not actually mentioned in this problem. That has to do with this point right there. Because this is a dotted line, because it's just less than or greater than, and because we have a starting point, right? It's not a continuous graph. that has to be an open circle. It's the same idea as the dotted line. If it's less than or greater than, and you put a point on a graph on a number line, then it needs to be an open circle. If it's one of these, it needs to be what kind of circle? Closed. So dotted line, open circle, solid line, closed circle for the endpoint. The domain on this one is x is greater than negative 2.5 because the inequality is less than, which means, so if you take a look here, we would look at this and we would say, this needs to be greater than or equal to 0, right? So 2x plus 5 is greater than or equal to 0. So let's just go and do that math real quick. Because no matter what, underneath the square root has to be greater than or equal to 0. Otherwise, we get a complex or an imaginary value, which is not what we're dealing with. And so if you work through the math here, you'd subtract 5 from both sides. You get 2x is greater than or equal to negative 5. And if you divide by 2, you get x is greater than or equal to negative 2.5. That's what we would do normally, but because our symbol does not have the or equal to underneath it, that's why we need an open circle here, it turns into just greater than. So if you wanted to start by saying this needs to be just greater than 0, that's fine too. You don't have to have that or equal to. If it was an equation, we would need that, or if this was less than or equal to, we would need it, but because it's just less than, we don't actually need the or equal to underneath there. So that might be easier to start with not even having the or equal to if this symbol is just less than or just greater. Shade the region above or below? Below, yeah. And you can see that in yellow over here. Shade the region below the boundary and within the domain. Within the domain means you cannot shade to the left of negative 2.5 on the x-axis because this graph doesn't go left of negative 2.5 on the x-axis. It doesn't actually get to negative 2.5 on the x-axis. In fact, it might be a good idea, and this is, sometimes I'll do this when I'm working on boundaries because it says shade below the boundary within the domain. Within the domain would be the line, you'd have x is greater than negative 2.5. That's the domain, right? X is greater than negative 2.5, which is here. Now, if you're going to put that on your graph, that would be a vertical dotted line at negative 2.5. So sometimes it's a good idea to also go ahead and just put a boundary right there. Because anytime you're talking about an inequality, it's an area, it's a region where those points could be answers. Everything in this yellow area is an answer to this inequality. And so if you put a boundary for the vertical boundary, because nothing can go to the left of negative 2.5, that might be a good thing to put on your graph. You don't have to, but it also creates a nice visual boundary for where that can go. And then it says, select a test point in the shaded region to verify the solution. So basically it says, when you're selecting a test point, make sure the point is within the domain of the related function. So basically, any point in this yellow area, take a value of x, plug it in here, and see if it works with the corresponding value of y. So for example, if we chose the point, let's use a test point right here. Doesn't really matter. Just pick one at random. That's the point 3, negative 2. So if you plug in 3 for x, 2 times 3 is 6. 6 plus 5 is 11. The square root of 11 is 3.3. So if you think about it, the y value here is negative 2, isn't it? Is negative 2 less than 3.3? Yeah, so it works. So that test point works just fine. which means that this has been graphed the way it needs to be graphed. If we chose any point out here, those would not work with that inequality. All right. Cube root functions, and then we'll be done. This will actually not take all that long. Actually, you know what? No, we do have more after that. Sorry, this is a long lesson. Good grief. Okay. Graphing cube root functions. A cube root function is a radical function that contains the cube root of with a variable of the expression. Like square roots have square roots in them, or have the variable in the square root. All right, the parent function of the cube roots is f of x is equal to the cube root of x, or y is equal to the cube root of x. That's what the graph looks like. It's like an S. This one is a little bit different than square roots, obviously, because you can have negative values of x. You don't need to restrict the value underneath the radical because you can have negative cube roots. If you put a -1 in for x, the cube root of -1 is -1 because -1 times -1 times -1 is -1. So you can have both positive and negative values underneath here. We don't need to worry about having values that are strictly greater than 0 or greater than or equal to 0 because it could be anything. Which means that the domain of this function is all real numbers. The range is all real numbers. It goes left and right forever. It goes up and down forever. If we have intercepts on this particular function, the graph crosses right in the middle of the graph at 0, 0. So the x-intercept is 0 and the y-intercept is also 0. We're talking about end behavior. As the graph approaches negative infinity on the x-axis, it goes to negative infinity on the y-axis. As the graph approaches positive infinity on the x-axis, it goes to positive infinity on the y-axis. If we are talking about increasing and decreasing intervals, this graph increases as x goes to infinity. So if you go from left to right, the graph is always moving in an upward direction. The speed at which it increases changes, but it's always going up, right? It never actually turns back down and goes the other way. So it's coming in pretty shallow, goes up really steep right here, and then it kind of shallows out after it gets past 0. But it's still increasing the entire time. The graph is positive above the x-axis, positive y values, when x gets past 0. It goes from negative to positive as it goes past 0 on the x-axis. And then it's negative for all the negative values of x. So y is positive when x is positive, y is negative when x is negative. This one has symmetry, unlike our last one. Square root graphs don't have symmetry. Cube root graphs do have symmetry. This one is symmetric about the origin. Basically what that means is, if you were to rotate this around like that, if you were to rotate that whole thing around the origin, you would end up with it right on itself. Or if you were to take this one here and rotate it back up that way, it would rotate right onto itself. So symmetric about the origin means it's a rotational symmetry. It's not symmetric about a line. There's no line that you can draw in and reflect it across. But if you rotate it 180 degrees, that will then cause that symmetry. All right. Questions about any of that? Cool. I'm going to put a little note here. 180-degree rotation around the point 0, 0. Now that point can definitely change depending on where the value is from when the graph goes from, well, basically when it does its little s, right? I was going to say positive to negative, but that isn't necessarily true of all of these. So we'll see as we go through these. So the cube root of a function can be written exactly like the square root of a function, except the index is 3 instead of 2. Everything else is the same. All right. So if we were to graph this function here, this one's basically done for us. We're going to write in a few things, but not much else. So our value of a is what? 1/3. All right, a is 1/3, which means it is less steep than the original. It's a vertical shrink or a vertical compression by a factor of 1/3. Our value of h is what? 0. Yeah, there is no value underneath the radical with x, so h is 0. And k is, what's k? K is also 0. There's no number added or subtracted after the radical, so k equals 0. So the function is centered at the origin, 0, 0, and has been vertically compressed by a factor of 1/3. And then if we type this into our calculator, we could go to the table menu, and we'd see all these values here, and then we could plot those on the graph and do our little curve through it. Basically what we're talking about on that. Let's keep going. This one, we don't have to graph it, but we do have to come up with these values here. So we're going to go back to our graphing calculators in just a moment. In this particular problem, we've got the cube root of x plus 5, which means that a is equal to 1 because there is no number to the left of the radical. H is equal to -5 because we have a plus 5 underneath the radical. And k is 0 because there's nothing added or subtracted afterwards. So this is basically the parent function, but it's been translated how? Yeah. Left 5. Because it's the same rules as transformations of a square root, which is the same rules for transformations of a linear, quadratic, cubic, any type of function. It's all the same rules, which is, just rules are consistent, which I find refreshing. All right, domain, all real numbers, range, all real numbers. By the way, that's going to be true of any cubic function. So let's get some values here. Y equals, let's go ahead and clear out that function there. We're going to have the cube root. So we need to go to the math menu. So hit math, scroll down to cube root, number 4. And we're going to type in x plus 5. Head to the table. Scroll back to -7. That's where we're starting. So when x is -7, y is -1.26. When x is -6, y is -1. When x is -5, y is 0, and then 1, and then 1.26 when x is equal to -3. That's all you have to do for that. Type in the function, go to the table of values. If you want to, you can go to the main screen and type in the function a bunch of times and plug in for the x values to get the y values, but I don't know, I feel like that's more work than needs to happen. So if you were to graph them, you get these points right here. Now this one, let me ask you this. Where is the point of rotational symmetry for this graph? -5, 0, yeah. So right here, that is the point of rotational symmetry. And if you notice, take a look at the middle of this graph. -5, 0. 0 is in the middle of this table. If you go 1 away on the left and you go 1 away on the right, you end up with opposite values for y. If you go 2 away on the left and you go 2 away on the right, you end up with opposite values for y. That's always going to be true. Take a look here. If you go 1 away on the left, 1 away on the right, opposite values of y. 2 away on the left, 2 away on the right, opposite values for y. What do you think would happen if a was negative? What's that? Yeah, this one would be positive, and then that one would be negative. They'd still be opposite for the values of y, but the whole graph would be reflected across the x-axis. So the whole thing would just be flipped over. Everything here would be underneath here, and everything underneath here would be up here. So it would start up here and then come down and go down like that if the a value is negative. In fact, example 6, we'll see that, but not on part C here. So let's see. The function can be written. Oh, hey, take a look at this one. This one's a little bit weird, huh? So we got the cube root of 4 minus x plus 1. Now, the reason why it's written like this is because, generally speaking, we want our variable to be the lead term underneath our radical. In our radicand, the lead term should have x. So what we can do here, I'm just going to go ahead and say equals the cube root of, let's go ahead and swap the negative x and the 4. So that would be negative x plus 4 underneath here. Like that. And then plus 1, which in turn turns into the cube root of the opposite of x minus 4 plus 1, because they factored out a negative from the x and the 4. And so they wrote it like that. So this function is translated, or sorry, reflected. Where is it reflected though? Because the negative is on the inside of the radical, how is this one being reflected? Is it x-axis? It's y-axis. Yeah, it's been reflected this way. So I'm just going to say, let's be a little bit more specific here about the y-axis. So this one's been reflected about the y-axis because the negative is with the x on the inside of the radical as opposed to the left of the radical altogether. If it was to the left of the radical altogether, that would be a reflection across the x-axis. On the inside, it's across the y-axis. So we've got the opposite of x minus 4, which means it's been translated 4 units to the right because h is positive, because the minus is part of the function altogether. And then plus 1 means it's been moved 1 unit up. So it's a y-axis reflection, 4 units to the right, 1 unit up. Which gives us, right here, that is our point of rotational symmetry. Which means as we go, 1 to the left and 1 to the right, these become, well, they would become opposite values of each other if it was centered on the x-axis, but that's not necessarily true here. Same thing here. These are not opposite values of each other because it's not centered on the x-axis. It only works that way if it's centered on the x-axis. But these are the points that we've got. We got our point of rotational symmetry. Now it's coming in from the top and moving down and going down to the right. The domain is all real numbers. The range is all real numbers. You're going to see that as a pattern when you're talking about not cubic, but cube root functions. All right, next one, comparing radical functions. Examine p of x, which is equal to negative 2 times the cube root of x minus 6 and q of x shown in the graph. So part A, make a table for the values of p of x. So p of x is the cube root function. Q of x, does that look like a cube root function to you? For q of x? What type of function does that look like? This one's cube root, p of x, that one. Q of x here looks like what? Looks like square root to me, yeah. All right, so for part A, if we compare these, let's just go ahead and graph, because we actually have the function written out for p of x, so let's go ahead and graph it based on this, and then we'll figure out what's going on with q of x in a minute. So we're going to graph this one, make a table of values. So here's the table of values, it just gives it to you. You just type in the function, go to the table. And then all our values here, we know it's been moved 6 units to the right because of the minus 6 here. So that's why 6 is in the middle. Thank you. So we know it's been moved 6 units to the right because of the minus 6 under the radical symbol. So that's our point of rotational symmetry right here. And then all the other values here are approximate, and we just graph it. All right, flip the page. Comparison of key features here. The domain of the cube root function is all real numbers. The range is all real numbers. This is going to be kind of annoying because we're going to have to switch back and forth. The domain of q of x, if you take a look here, all the values for q of x are either 6 or greater than 6. So x is greater than or equal to 6. Right there. The range starts at 0 and goes down. So the y values are less than or equal to 0. That's right there. The x-intercept for each of them is 6. because they both come into contact with the x-axis at 6 here and at 6 here. However, the y-intercept of P of x is 3.63. When x equals 0, y equals 3.63. That's the y-intercept. This one does not come into contact with the y-axis. Therefore, there is no y-intercept where this one is 3.63. The increasing and decreasing. This one decreases as x goes to infinity, and this one decreases as x goes to infinity. Neither of them have increasing intervals, because as you go to the right, this one goes down, and this one here, as you go to the right, it goes down. So they're always decreasing for both of them. Positive and negative intervals. This one has positive intervals left of 6 on the x-axis. This one has negative when you go right of 6. So after 6 on the x-axis. This one only has negative values for y after x equals 6. And then the end behavior, as x goes to positive infinity, P goes to, as x goes to negative infinity. As the graph goes left on the x-axis, y goes up to positive infinity. As it goes to the right, positive on the x-axis, P goes negative. This one here, as x goes to positive infinity, P goes to negative infinity. Now, if you go left on this one, you'd say as x approaches what? How far left does it go for Q of x? Take a look at the Q of x graph on the previous page. How far left does it go? What's the smallest x value? 6. So as x approaches 6, what does y approach? 0. Good. So that would be the other end of that one. So essentially what we're looking at here is this graph here is probably the same as this one, except it's a square root instead of a cube root. Let's see if that's right. Go to your y equals menu. Let's type in, let's do the cube root first. So the cube root of -2, -2 times the cube root of, not cube root first. -2 times the cube root of x minus 6. All right, we got that. Go to the graph real quick, and we should see that P of x graph that's on our paper, and sure enough, it looks great. It looks exactly like it should. Now, if you then go ahead and say -2 times the square root of x minus 6. Let's see if this one matches, but only, hey, not quite. So it's a little bit different. So what do you think is different here? What's that? Yeah, the cube root and the square root change the values a little bit. They look pretty similar, but they're not going to be exact. So if you look here, if x is positive 10, y is -4 on this one. And if you look on this one, if x is positive 10, y is -3. So cube rooting a value decreases that final value by a little bit, enough to the point where the curves are going to be a little bit different. So, but actually, that is the graph of this, though. They don't match each other, but this is the correct red graph, even though they're not matching. Because if you go to 10, 7, 8, 9, 10, down 4, 7, 8, 9, 10, down 3, that definitely matches with what we've got here. So this is Q of x is this particular function, but it's square root instead of cube root. All right. One last problem, and then we are good to go. So writing a radical function. So we're going to have to write the function based on the graph. So first of all, we're going to identify the index, which that is basically figuring out if it's a square root or a cube root. That should be a pretty easy part to do here, right? Is this square root or cube root? Cube root. Index is 3. Because it goes to positive infinity and negative infinity both on x and y. It doesn't have a starting point and then going, just a part of a curve. So this is the type of function we're going to be writing. Identify any transformations. The function has been translated 3 units left and 4 units down. So start with the easy transformations first, which would be the movement, right? Our point of rotational symmetry is here. That will tell us how far the graph has been moved. It's moved 1, 2, 3 to the left, and 1, 2, 3, 4 down. Look for that point of rotational symmetry, and that will give you the translation. So the value of h, if you go left, is that a positive or a negative movement if you go left? Negative, so -3. And then k, up or down? Down 4, so -4. So we have h, we have k, we have the index. We don't have a. So to find the value of a, use a point on the graph as well as the values of h and k, which means you cannot use the point -3, -4 for your x and your y values because those are already being used as h and k. So this one is suggesting that we use, looks like -2, -2. And so what you should be looking for in this case for an xy value is any value that is clearly whole number or integer values for your x and your y. And -2, -2 right here definitely goes through integer values for x and for y. So that's the point it's suggesting to use for x and y. So we got xy here, hk here. And then substitute in and solve for a, because out of this entire function, g of x, a, x, h, and k, we have g of x, which is the y value, which is -2. We don't know a, that's what we're solving for. We know we've got a cube root. We have an x value of -2. We have an h value of -3. We have a k value of -4. And so we have 4 out of the 5 values, which means we can solve for the one that we don't know yet. So let's see, -2 minus -3 would be -2 plus 3. What's -2 plus 3? Yeah. What's the cube root of 1? 1. So -2 is equal to a times 1 minus 4. A times 1 is a, right? So this is just a minus 4. So to get a by itself, we would add 4 to both sides. To get a by itself, what's -2 plus 4? 2. So +4 plus 4. Those 4's cancel. -2 plus 4 is 2. So a is 2. So we have an h value, we have a k value. Now we have our a value. And then when we write our answer, we don't use the x, y value that we used earlier to figure out a, because we want generic x and y. So when we write our answer, we're going to use g of x instead of that -2, and we're going to use regular x instead of the -2. So it's going to be g of x is equal to 2 times the cube root of x plus 3 minus 4. All right, let's try the last one here. Where on this graph appears to be the point of rotational symmetry? 1, 2. Good. Which means, let's go ahead and do some work off to the side here. H equals what? If it's going to the right one, H is what? 1. K equals what? It went up 2. K is 2. Okay. Is this a cube root or a square root? Cube root. Okay. So we have HK. Find another XY pair that is clearly integer values. Where's a point on this graph other than the point of rotational symmetry that is clearly identifiable? I see 2 of them. Where's a clear point on this graph where x and y are both integer values, whole numbers? 2, 5. I like it. That was one of them. The other one's the y-intercept at 0, -1. But yeah, 2, 5 is great. Let's use that. So say x is 2 and y is 5. So here we go. Y equals 5. So we're going to say y equals, not y equals, 5 equals the a, we need a, because that's what we're solving for, the cube root of our x value is 2. Our h value is 1, so 2 minus 1 underneath that. I'm going to get rid of that. Plus 2. That 2 is not underneath the cube root. Sorry, I extended that way too far. All right. So x is 2, h is 1, so we leave this as subtraction. We put a plus 2 on the outside. Y equals 5. We're solving for a. I should not have extended the cube root as far as I did. That plus 2 is on the outside of it. What's 2 minus 1? 1. What's the square or the cube root of 1? What's a times 1? A. So this is 5 equals a plus 2. So what does a equal? 3. Yeah, a equals 3. So we are writing the function of g of x. So we're going to say g of x is equal to what? Let me give you the function. Three. Cube root. What goes under the radical? Minus 1. What minus 1? X. X minus 1. And what goes after? Plus 2. Cool. Just to verify, we got a few minutes left here. Here's something you can do to make sure you've got these right. If you're writing a function based on a graph, type it into your calculator and check it with the graph. So,
May I have your attention, please? Just note that all tennis matches scheduled for today have been canceled and will be rescheduled.
Because of the
Again,
rain.
all tennis matches scheduled for today have been canceled and will be rescheduled.
That's a bummer. So 2 times the cube root of x minus 1. Sorry, 3 times. Why did I write 2? 3 times the cube root of x minus 1 plus 2. All right, graph. Let's see if these look the same. I'd say those look pretty similar. I'm going to go ahead and change things just a little bit, though, because I want to match my window here, or relatively match the window here. So I'm going to say z square 5. I mean, they definitely have that pretty much the same shape going on. You can really check if you go to your table of values, because we know we've got a point at 0, -1. There's 0, -1. We know we have a point at 1, 2, there's 1, 2. And we know we had a point at 2, 5, there's 2, 5. So we're set. Nice. So your assignments. Got about 3 minutes left today. So this is definitely going to be some homework. And then let's see. These all look pretty good. We're going to do 1 through 41 odds. So 1 through 41 odds. You will need graph paper, by the way. So I would highly recommend coming on up here, grab some graph paper before you leave.